While the fundamental nature of science might be similar to the way an intelligent animal uses its senses to explore and learn about its world and start to make meaning, when we extend our science with more detail and rigour and design an experimental process, we do take it a step further. We're now going to start to work on an investigation that goes right back to the beginning of this program, when we were watching across the inlet the steam coming up off the sea on a cold morning and thinking about density, thinking about the warmth that must have been in that sea for that evaporation to occur into the cold water. Background is all the detail and information we can find out by exploratory science, just going out and seeing and finding out things, exploring. It's by observation, it's by personal communication, and it's also by doing our background reading and research into what other scientists and science has done. Once we've done that, we can come up with a question. We can ask us that curiosity, that foundation part of science. A question is a good operational tool. It's the scientist's main tool. So we can ask our question is, how is it that there's evaporation and moisture coming off the sea, indicating that warm water? Is the water warmer in the large ocean mass? Does mass affect temperature, the increase in temperature or decrease in temperature over time? And so from there, we come up with a working statement. We say, okay, these are our questions. What do we think? What is our best statement, the one that holds the maximum truth value with what we know at this point in time? And this has become called the hypothesis. So this is our working statement at which we think holds value. We need to test this. We need to actually check what is the truth value of this statement. And to do that, we've got to think about validity. Okay? Validity is a really important part of it. Now, what is validity? What do we find when we break down validity and look at it in more detail? Well, it involves context. So we have to do it in such a way that we use the same materials, similar scales, or some comparable scales, or something that is scalable, that we can relate to the context we're really interested in, which is this ocean mass. We're going to use water. Content, like the content of our statements and the content of the data that we collect needs to be relatable to the real world that we're trying to make these statements about. And does it make sense and meaning, not only in terms of its own internal sense and meaning in the statement, you know, is it a sensible statement, is it reasonable, but in terms of science's knowledge at this present time, does it have sense and does it make meaning within the whole body of science knowledge at this present time? And a lot of this is to do with time and place. We need to be able to collect data over sufficient length of time, at a time, and in locations that are comparable or allows us to compare it with the context and the content we are really focused on, the ocean. The next part is reliability. Now reliability is to do with how rigorous we do the investigation and how confident we will be in the data we actually collect at the end of it. The parts of reliability that are important are what are the treatments we're going to use. While the types of treatments we do are part of validity, the range of treatments and how many treatments we do are part of our reliability. We also have to really look at this part here, replicates. This is your old idea of sample size. So let's start thinking about that. Here's the truss of treatments. We're going to have some small containers. Okay, we'll have a small one, about 1 litre. Now, luckily enough, I've got a container here that is about 10 litres, so I can multiply that by 10. I've got this barrel here that allows me to do 50 litres. 50 litres, 10 and 1. That should be a good comparison. 50 times, 10 times, 5 times. I'm going to label these treatment 2, this one here, treatment 3, this one here, and this is treatment 1. Now, ideally I would have multiple replicates of each one, but unfortunately I've only got these containers. I'm going to reject this one, so and I could include this one. So if you don't have 3, 2's okay. You might have a 10-litre bucket and a 1-litre container here. I will reject this one. Now you might wonder, why am I rejecting these? We've got to think in terms of reliability. Any other system error. One of the most terrible errors that can occur is if we have multiple variables that are overlapping and so confuse or confound our results, and we call these confounding variables. So what will affect temperature change may be the colour. G'day, here's Dudley the science duck. He's pretty keen on the old water thing. It could be that black is going to absorb more heat, and that might influence it. So if we compared these two, there would be a confounding variable, and we don't want that. We're trying to keep them all dark. I am going to have a repeat, a replica of the 1 litre, and I'm going to label those replicate 1, replicate 2, treatment 1, and replicate 3, treatment 1. So I do have 3 samples for that treatment. Yeah. Now the other thing that is important, of course, is our system error and our instrumentation, but we're going to stick with multiple instruments, and we know that Kevin is a really sensitive, wide-ranging and reliable instrument. Time, timing and place. We're going to keep them all in the same place. We're setting up for tomorrow. Tomorrow is predicted to be another nice sunny day. We're going to run a time sequence from morning through into the evening, and we're going to give enough time for a temperature change to occur that we can measure, and enough time for each of our instruments to reach equilibrium at each measurement. So we're going to plan and design something that starts around at 10 a.m. in the morning, finish 10 p.m. at night, and maybe try and measure it every 2 hours. This may be a trial and error thing, and we may find 2 hours is too soon. We might have to do 4 hours, but we're going to try that anyway. Ideally, built within the design would be the opportunity of repeat. So we not only do it once, the whole thing, twice, 3 times, and the more we replicate, the bigger our sample size, and the more we repeat, the more reliable our data will become. Obviously, we're right down at the lower end of a range of treatments, so we're going to add value to this. We're going to actually include some exploratory fieldwork, and we're going to go down to the inlet. We're going to measure the temperature of that huge bulk of seawater coming into the inlet and the air temperature down there as well, and see how those two compare and change in relationship to these.